Okay, we're going to do 9-3 first half, so 9-3A. And we're going to talk about sequences. And I'm not talking about those sparkly things on your prom dress. Aww. I know. Sequences. So we're going to do some patterns today. Do you like patterns?
Can we just play the game sequence?
Sequence. What is that? That's a game?
Yeah.
I've never played that game.
Really?
Yeah.
Oh.
All right. That's fun. Is it an app?
No. Well, maybe. I don't know.
Oh. All right. Let's talk about what a sequence is. You'll have to tell me what this game is. It's fun. Is it math?
Kind of.
Okay. I'm in. I win. No, I'm just kidding.
We'll play 5 in a row with cards and tokens. But it's not poker.
Oh, you're gambling? I'm sorry, I'm out. Nope, I don't gamble.
No, it's
No.
not poker. But
Oh.
you have cards. And you have tokens.
Tokens. All right, so what is a sequence? Well, a sequence is just an ordered progression of numbers. Ordered numbers. There's a sequence feature on your calculator. Do you remember when we did calculator, we went to mode, and there's function, parametric, which we've done function and parametrics. There's polar, which we'll do second semester. That's the stuff over here. And then there's sequence. There's a sequence mode. I never use it. I don't really like it because it's weird to me. I don't know. There's like a minimum and then, but you know what? All sequences are functions. So I just keep it in function mode and just use that. Okay? All right. So let me give you an example of what a sequence is. So it's just ordered numbers. So here would be, there's two kinds of sequences. You can either be a finite sequence, like this, 5, 10, 15, 20, 25, and stop. It's a finite sequence. It has a finite number of numbers in it. It has 1, 2, 3, 4, 5 numbers in the sequence. You could also have an infinite. Infinite. How come we don't say infinite? An infinite number of numbers in a sequence, like 2, 4, 6, 8. We appreciate, yeah. And then you put dot, 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 dot. And that means that you will have it go forever and ever. Okay. Now, for these sequences, we have two ways that we can write the formula for these, okay? There's an explicit formula. Explicit. And an explicit formula will describe the kth term. Your book likes to use K. Your Algebra 2 book likes to use N, the nth term. They like to use the kth term. Okay? It's a function that it's a function. You write it as a function. And basically what it does is that assigns a unique number to each natural number k. A function that assigns a unique number, they'll call it this. They'll call it a sub k, okay, to each natural number k. To each natural number k. I'll explain what explicit is when we do one. So let's just do one right away, just so that, you know, this looks kind of confusing and like, what am I talking about? So, number 1. Suppose that they give you an explicit formula for a sequence. Explicit formula would look like this. A sub k equals k squared minus 1. K squared minus 1, okay? What this does, this is going to give us a sequence, and we can find, let's say A says to find the first 6 terms. Find the first 6 terms. Why is this really hot in here now? This thing's going to blow up. All right, so if you want to find the first 6 terms, you let k equal 1, k equal 2, k equal 3, all the way to 6. And then you'll find them. So see, it's a function that assigns a unique number to each natural number k. Natural numbers are counting numbers. They start with n equals 1 or k equals 1 in this case. So when k equals 1, what do I get? 0. When k equals 2, I get 3. K equals 3, 8. And it's all the perfect squares minus 1, isn't it? The next one would be 15. How many is that? 4? 5 would be 24, and 6 would be 35. And that's where you end. Okay? Now, explicit is the best way to write things, I think. There's going to be the other way, which we're going to talk about. But explicit can get you to whatever term you want. What would be the 20th term of this sequence? I don't need to find all 19 before it. I can go straight to the 20th term by plugging in. See, the 20th term would be this. A sub 20 equals 20 squared minus 1, which is perfect. 399. That would be the 20th term. Okay? All right, so that's explicit. Now, the other way to write things is the way that you're used to doing them. And that would be recursive. This is the way that you learn to do them when you're in elementary school. Like I was helping my son with his math homework, which I love to do. I'm sure he does too. No. But they always tell you, find a pattern here, what's going on. And he would always do, oh, I'm adding 2 to get the next one. He relates it to the one before to get the next one. Instead of an explicit formula, he does a recursive formula. So a recursive formula, what this does, it does a value for the first term. It gives you a value for the first term. Gives you a value for the first term. Or terms. Sometimes they might give you the first term and the second term. And then a formula relating to the previous term. Relating to the previous term. Now, this stuff sounds kind of familiar. It's because you did it last year. We did a whole chapter on sequences. Sequences and series. We did arithmetic and geometric, and we're going to get to those again. Right now, this is just in general, just sequences in general. So let me show you an example of a recursive formula. Number 2. B sub 1, and they can use whatever variable they want. B sub 1 is 3. Okay? And then B sub n is equal to B sub n minus 1 plus 2. Now, this always looked confusing to me when I was your age and I tried to do these problems. I would get so caught up in I need to plug 3 in for n or plug whatever in. No, you're not going to do that, okay? What you're going to do is you're going to think of this. They give you the first term, okay? So that's nice. That's the first term of your sequence, okay? Then this right here, this b sub n minus 1, is just going to be the term before. This is called the previous term, bless you. So whatever term I'm trying to find, that b sub n minus 1 is the previous term. See, if I have b sub n, what's the term right before it? It's b sub n minus 1. It's the term right before it. So if I want to do this problem and I want to find the first 6 terms, okay, I would start with 3. 3 is my first term. And then I need to find 5 more. So what I do is I take 3, and what this right here, what this formula is telling me is to take the previous term and add 2 to it to get the next term. So how do I get this term right here? I add 2 to the 3. So that would be 5. How do I get the next term? Add 2 to 5 now to get 7. Do you remember doing these? And then 9, 11, 13. Find the first 6 terms. Now, if I had to find the 100th term, that would be terrible. Okay, I wouldn't want to do that. Not within a recursive formula. Okay, I wouldn't ask you for the 100th term. And let's just erase this A right here because we don't need that. There you go. Okay, let me give you a famous sequence. It's called the Fibonacci sequence. Have you ever heard of Fibonacci?
Yeah.
Fibonacci sequence. And the Fibonacci sequence, you can write it recursively or explicitly, but most of the time it is written recursively. Okay, and so the Fibonacci sequence is a sub 1 is 1, a sub 2 is 1, and to find a sub n, you take the previous term and add that to the previous term. Right? Yeah. So if you know the Fibonacci sequence already, you got this. If we're going to write the first 6 terms, let's just go first 5 terms. First 5 terms. Oh, they already give us 1 and 2. Oh well. Okay, first 5 terms, it would be 1, 1. The Fibonacci sequence tells me to find the next term. I want to take the term before it and add it to the term before that. So what would my next number be? 2. Now take the term before that and add it to the next one, which would be 3. 2 plus 1. Now 3 plus 2 is 5. Let's keep going. 5 plus 3, 8. 8 plus 5, 13, so on. I have a little poster. Oh, man, I took my poster away? I did, yep. Okay, I don't have a poster anymore. Oh, I put up my paintings, right? That's more important. Okay. Anyways, this Fibonacci sequence is actually found in a lot of different things. In nature, it's like when you count some spirals of a pineapple or something, and actually these numbers show up. It's really cool. Yeah. Okay, that's part A. That's just describing what a sequence is. How do you know what a sequence is? Stuff like that. Now, part B, last part, is we are going to talk about the limit of a sequence. Limit of a sequence, okay? All right. So we've done a little bit about limits, right? You didn't like them so far? We're going to do some more here. We are going to find the limit of a sub n, the terms of a sequence, as n goes out to infinity. Okay? We're going to have a sequence of numbers. So our sequence would be like this: a sub 1, a sub 2, a sub 3, a sub 4. And we're going to take it all the way out to a sub n plus 1. It's going to go as far out to n goes to infinity. We want to see if our sequence is going to do one of 2 things. All right? The sequence is either going to converge. Okay? It will converge if the limit as n goes to infinity for these numbers is an actual number L, a finite number, okay? It will converge. Now, the sequence will diverge, so it can either converge or diverge. It will diverge if the limit either does one of 2 things. It either does not exist or it goes to infinity itself, plus or minus infinity, really. Okay? Okay. I'm going to give you a couple of examples of these. So here we go. Number 3. All right. The book says to find the limits, determine whether the sequence converges or diverges. If it converges, give the limit. So we're going to see converge or diverge. And if it does converge, then we want to find the limit of the sequence. All right, so here we go. Letter A. Let's say we have a sequence that does this. We have 1 over 1. Then 1 over 2, then 1 over 3, 1 over 4, dot, 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 1 over n, dot, 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 keeps going, okay? So that would be our formula, 1 over n. So we want to find out if this sequence is going to converge or diverge. And if it converges, we have to find out the number, Okay? So what you want to do is you want to take the limit. You want to find the limit as n goes to infinity for this formula right here. They gave you the formula for your sequence, which is 1 over n. Okay. Now, do you remember what 1 over n was? 1 over n? It's one of those rational functions. Watch, if you take infinity and let's say you plug it in for n. What is 1 over infinity? It's a huge number on the bottom, right? Teeny number up top, 1 over infinity. This is going to, anyone want to take a guess? 0. Yeah. So this sequence, I always think of it in terms of graphs though, converges to 0. Okay? You get 1 over 1, then 1 over 2, 1 over 3, 1 over 4, 1 over 1,000, 1 over 1,000,000. What are these numbers getting closer and closer to? 0. All right, let's try another one. These are a little confusing, huh? All right, B. Let's do this one. 2 over 1, this one's going to be tricky. 3 over 2, 4 over 3, 5 over 4. So you see the pattern. This time they didn't give it to you in terms of n. So the nth term is not explicitly given to us. We may want to find that. You could also, you know, like get your calculator out. This is kind of an kind of way. And you can go 5 divided by 4, 6 divided by 5, 7 divided by 8, right? Wait, no, I'm doing that wrong. 5 over 4, 6 over 5, 7 over 6, right? 8 over 7. Okay, and you might be able to tell what the numbers are getting closer and closer to, but that's a little sketch too. It's like, you're just kind of guessing. So we want to make an explicit formula for this. All right? Our explicit formula means that we want this to be in terms of n. So what, and when you have fractions, split it up. There's a bottom sequence and there's a top sequence. The bottom sequence is pretty easy. What's it doing? 1, 2, 3, 4. So that would just be n. My first term, I get 1. My second term, I get 2. My third term, my fourth term. What's the top going to be?
N plus 1.
N plus 1. Yeah.
Oh, is the top dependent upon the bottom?
Yes. And this, well, I look at them as separate sequences. So there's a bottom sequence of 1, 2, 3, 4, 5, 6, 7, which is just n. And the top one is just one more than the bottom. So if I get the bottom, I can just relate the top one as n plus 1. All right. So do you remember asymptotes?
Yes.
Okay, here we go. Horizontal asymptotes. When the limit as n goes to infinity of anything like a sub n, this is going to be our horizontal asymptote. We learned this in chapter 2. Now, look at this sequence. N plus 1 over n. Think of it as a function, like x plus 1 over x. What is the horizontal asymptote of that function?
1.
It's 1. And so our limit would be 1. So this converges. Do we need to go back and look over the horizontal asymptote, those 3 cases? We probably do, huh? Let's do one more of these, and then we'll talk about the 3 cases, okay? All right, last one of these. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12, ... Okay, you can come up with an explicit formula for this, but look as you're going off to infinity, your numbers are going where? As I keep going out for n equals 12, 50, 100, 1,000, my numbers are getting larger and larger without bound, right? They're not bounded by anything. So this one would diverge. Okay, the explicit formula for this, does anyone know what the explicit formula for this is? 2n. Plug in infinity for n. Take the limit as n goes to infinity. What do you get? 2 times infinity, right? That's what you always say to like your brother. Like, you're infinity stupid. You're 2 times infinity stupid. Yes?
How is it 2n if it's, okay, so from 2 to 4, that's 2n, but from 4 to 6?
Yeah, so you have to think of this as explicitly. So this is n equals 1, n equals 2, n equals 3. So you're really relating these numbers to each other and not the numbers before it. That's recursive. For these, we want to do explicit. So how do I get, when n is 1, to get to 2? I just multiply it by 2 to get to 2, so on. Yeah, I know it's hard to switch back and forth between those. Okay, so let's go ahead. You know what? Without like really doing the, what number are we on? Number 4. Without really doing the asymptotes, we're just going to do them here, and you'll see what I mean by this. Okay. Find the limits of sequences. Determine whether a sequence converges or diverges again, but this time they're going to look a little bit differently. Okay? And I have 3 of these, and they're going to go really quick. So we have 3n over n plus 1. Instead of giving you a sequence of numbers, they actually give you the explicit formula. This one would be 5n squared over n cubed plus 1. And c would be n cubed plus 2 over n squared plus n. Okay, I gave you one of each. Write those down, and then we'll talk about that. So we're trying to find out if these sequences are going to converge or diverge, and if it does diverge, we want to find the limit. So we're trying to take the limit of the sequence as n goes to infinity. Okay? So, and that's going to equal my horizontal asymptote if there is one. Horizontal asymptote. So let's look at the top one. Okay? So what you want to do is you want to compare the degrees of the numerator and denominator. And if you look at this top one, that has an n up top and an n on the bottom. Okay? With a 3 in front. And so this one would converge to what? 3. It's leading coefficient over leading coefficient. Do you remember doing that with the horizontal asymptotes?
Yeah.
When their degrees are equal, so the degrees are both 1, it's almost like you have this. Let me show you. You have 3 infinity over infinity plus 1, okay? That infinity plus 1 is still infinity, right? You know, it's like infinity plus 1. It's still infinity. So if we ignore that and we take 3 infinity over infinity, the infinity is reduced and you get 3. Weird, huh? But that's a way to think about it. This next one, do you remember doing this one? The degree of the numerator is smaller than the degree of the denominator. So in this case, I have 5 infinity squared over infinity cubed. The plus 1 doesn't matter. We're talking out towards infinity. And so those will reduce, and I get 5 over infinity. What is that? 0. This converges to 0. Okay? And then the last one, the numerator degree is bigger than the denominator degree. And so you basically have infinity cubed over infinity squared. Don't worry about the plus 2 or even the plus infinity. It won't matter. Okay, you're way out in infinity cubed, infinity squared. This is going to infinity because that will reduce with one of those. And so this one would diverge because it goes to infinity. Those numbers are just getting bigger and bigger and bigger. It just diverges. Okay?